Hello and welcome to the discussion video for CS239, Week 3. I'm Alex. Today we'll be going over loss functions, KNN, Softmax, SVMs, as well as vectorization. Let's start by jumping right into loss functions. So our setup is the following. We have some data, x, of size n by d, where each example, xi, is of size d. We also have our labels, y, and we have n of them. And for the categorical case, such as in CFAR 10, these will be integer valued. And each one will take a value between 0 and c for C classes. In order to predict the labels of unseen data, and in order to assess our model performance, each model will have its own loss function, which is a way to quantify the error in the model's performance. One way to think of the loss is as a penalty for the model being wrong. And correct labels should incur 0 loss. Now for any model, the loss over the whole data set is just the sum of the losses over each example. So we can write this as a sum over I examples of the loss attributed to example I, which is some function of x parameters and the labels. Now, obviously, we want the most accurate model that has the smallest loss. If we could see the entire landscape of our loss function, then we could just find the best values by simply choosing the argmin. And that would lead us to theta hat, the best value for theta, which minimizes the loss. But since we can't observe the entire landscape, the best we can do is to just iterate over increasingly accurate estimates. Now, in order to reduce the error as much as possible, we want a non-increasing loss at each iteration, so a good loss function should help you to improve your estimate of theta. For example, by choosing a differentiable loss function, we can improve theta by using gradient descent. We can update our parameters theta by computing the gradient at some current theta coordinates, and then taking a step towards a region with lower loss. This is why we had vector derivatives assigned on homework 1. We need to compute derivatives of multivariate functions. Here's one way to visualize how our loss function works with our model. After each training iteration, we'll compare the outputs of the model, y hat, with the true labels y by passing them together into our loss function. And the output of our loss function gives us a signal that we can use to update our thetas. So in the case of gradient descent, we would take the gradient of the loss and pass this in to update the thetas, which should improve our model for the next iteration. By continuing to update our parameters, based on the gradient computed at the last theta coordinates, our goal is to hopefully converge to some argmin, and then our model will have improved in accuracy. Now let's review the details of some of the models that we've gone over in lecture. And we'll start with KNN. So for KNearest Neighbors, we have the following setup. We have our data, x, where each ith training example is dimension d, and we have labels, y, where each one is an integer. We want to assign a label to the new data point, x test. Then recall that for KNearest Neighbors, our parameters are k itself and the distance metric that we choose. Let's go over a quick example of KNN using an example where x is in R2. Right over here. So for each point, we want to compute the distance between here and all other points, and so on. So first we'll get the distances. Next we'll sort these, and we'll choose the nearest k of these distances. And then among these k, we'll take a vote to see who's the dominant class. And if there's a tie, we can choose either one, or maybe pick a point that's closest. So training the KNN model is pretty straightforward. We just store all of x and y. And when it comes to test time, again, we first just compute the distances, we sort them, we choose the first k of these sorted distances, and then among these we take a vote of the class IDs. And we assign a label to test point I based on the identities of his nearest k neighbors. Now let's talk about the distance metric. Consider these 2 points in R2. Here's V and point U. The distance between these 2 points is really the distance between these 2 vectors, which we can find by computing the norm of their difference. Suppose we had a whole collection of vectors stored in matrices U and V. Then in Python, for example, we could find the distance between all the vectors by looping over all the indices and storing the result. And that might look like something like this. Note that we have a nested for loop here, which will take on the order of n times m to complete. So we're going to want to vectorize this. So that means we want to compute all the distances in one shot without any for loops. And we might start by looking at this function here and seeing how we can rearrange it. But in this case, I'll leave that up to you. Next we have Softmax and SVMs. But first, let's recall the basics of linear classifiers. Recall for linear classifiers that we want to find some W and B, which maps from the input data to scores for each class, such that the value with the highest score is in the index of the correct class. So there's a couple of ways to think of linear classifiers. The first one is as a model that tries to find the best line which separates the data along a decision boundary. So in that sense, it's purely linear. And for higher dimensions, we would find a hyperplane. Another valid way to think of them is as an affine transformation, where our model is really a mapping from the input data to a vector of scores, where the value in each index represents the model's confidence that the training example belongs to the class associated with that index. Let's look at a quick example. Consider this binary classification task, where we have data in R 3x3, where y is either 0 or 1. So we have these O's and these X's. Then for a linear model, y equals wx plus b, and y is in R2, then our multiplication might look like this. If we reshape x into 9 by 1, then we'll have a multiplication of w, which is 2 by 9, times x 9 by 1, plus b, which will be 2 by 1. And the result will be a 2 by 1 plus a 2 by 1, and we'll have a 2 by 1 at the end. y1, y2, and these are the scores. Now, of course, the point of machine learning is to try to find the w and b that map from the input data to the correct scores, so that the value of the highest score is in the index of the correct class. For this example, you might notice that just by checking the center square, our model might quickly learn to distinguish between the two classes. But in the real world, data is much more subtle and complex. So that's where the value of the cost function comes in to help optimize these parameters. and that's where the following two algorithms come in, Softmax and SVM. Let's start with Softmax. So first remember that this AI of x is really wi transpose times x plus bi. So in this way we can consider softmax as a function that acts on linear classifiers. Or rather, it's a function that acts on the scores output by a linear classifier. In lecture we learned that the motivation for the softmax was trying to find a loss function to optimize so that we could turn a vector of scores into more powerful information that can help us tune our model. And one valid transformation onto the scores is to turn them into a probability distribution, and then use maximum likelihood estimation to find ideal values of theta. Now, since each softmax of I is between 0 and 1, and the sum over I equal to 1, and this forms a valid probability distribution, and so we can write the softmax as a probability explicitly, where this represents the probability that this data point, xj, comes from class I. Now the full derivation for MLE can be found in the lecture slides from lecture 4, so I won't write it all out here, but a couple things worth remembering are that we first write out the probability of seeing all of the data given our parameters theta, and expand this out into a joint probability, which we can express as a product of all the individual probabilities. And then we can use the chain rule to write this as the product of these two probabilities. Now, since our data set is fixed, x is the same no matter what values we choose for theta, then the probability of x given theta is a constant. So, probability of xi given theta, since they're independent, is equal to just the probability of xi. And for MLE, we're taking the argmax, and the argmax will be the same whether or not we have this constant in there. So we can just take it out. And that lets us write the likelihood as a product over I of yi conditioned on xi and theta. Now the next tricks we used were to take a logarithm, and we know that a log of a product becomes a sum of logs. And finally we arrive at our loss function. Now let's discuss the gradient of softmax by just recalling a few identities. So first, the derivative of e to the f of x equals f prime of x times e to f of x, and the derivative of the log of some g of x equals g prime of x times 1 over g of x. Now let's dig into SVMs. So the goal of SVMs is to find a boundary with the maximum margin, which is the distance away from the separating hyperplane. So there's two main concepts here. First, we want to find this boundary, which should be as far away as possible from points on either side, measured by this distance. And we want to find some margin, which is a hyperparameter, the length of which we want to seek. Now we want to be able to generate from our training set as much as possible, so we want to find the maximum margin that's as far away as possible. If our model finds a hyperplane inside of which there is a lot of space between adjacent points of opposite classes, then chances are good that new data points will also be far apart, even if they're unseen and end up in coordinates that our model hasn't been exposed to yet. So naturally, for any data points on the wrong side, we want to incur a big loss. So this means our model messed up, or just that the data isn't perfectly separable. most of the time you'll find it's impossible to have exactly zero loss. Now, if the ideal case is to have all the data points outside of the margins, then it makes sense to punish any points that land inside the margin, even if they're on the right side. So all these points that are still on the right side, but still are falling within these margins, will incur a small loss. And for any point that's on the right side, as long as they're outside of the margin, they'll get zero loss. So that's these guys. So you'll notice that this model either penalizes points or incurs zero loss, depending on the location. So, for example, there's no reward for this point being outside of the margin. Instead, we just assign a positive loss or zero. So naturally, you might think that there's some function involving a max involved. And of course, let's take a look at hinge loss and see how it works. This is the form of hinge loss for SVMs. If you allow me to take a shortcut in notation, then we can write it concisely in this form. Now let's do a quick example. Let's say we have a 3-class classification problem, and that our model just output the following scores: 6, -2, and 5.5. And for this training example, let's suppose that class 0 was the true class of the training example. In that case, we can write that yi equals 0. So let's work this out. We're going to sum over the wrong class indices, right? When j is not equal to 0 in this case. And we're going to take max of 0, 1 plus a sub j minus a sub 0. And that equals max 0, 1 plus, for this first one we'll do -2. And then we subtract a0. And then we'll add our next index, 0, 1 plus our last index, 5.5 minus 6, which comes out to 0.5. So for this output, given that the true label was the first one, we incur a loss of 0.5. Notice that even though if we took the argmax of this output vector of scores, we would get 0. So it looks like we got the right answer. But still, if you look at the last one, this one guessed pretty high too. So this should incur a loss because it's less than one margin away from the score that was output for the correct class. Earlier we said that the loss function for a model is just a sum of the loss of each training example. So let's write the SVM loss function. So if this is the hinge loss for one training example, then the loss over the entire data set we can find by just summing over I of the hinge yi of xi. And we can divide by m. And now to find the best estimate of theta, we can take the argmin, the whole thing. Now when plotting out the hinge loss function, remember that we have 0 loss for any data points on the correct side, as long as they're past the margin. So the ones that are in the margin will start to incur some loss, and past the margin on the wrong side will start to incur an increasing loss. Now when considering the gradient of the SVM loss function, we can see by inspection that there is a region with 0 gradient and a region with linear gradient. Another thing to note is that our loss function is in the form of a sum of individual hinge losses, so we can write the gradient with respect to parameter theta sub k of the loss function as 1 over m times the sum of the gradient of L sub I. Finally, let's get into vectorization. So a common function to vectorize is the dot product, where for each I entry of u and v, I'll sum ui times vi. And we can do this with a for loop, or we can do it vectorized, which we'll check out on the next page. Similarly, for a matrix product, A times B, dot product of matrices can be computed through a nested for loop, where we loop over I, and then loop over j, and we append the ij entry of our answer with the product aij times bij. Now in each case, whether multiplying two vectors or two matrices or what have you, rather than using for loops, we can evaluate these expressions by using built-in functions for NumPy. So we can either use the dot function, np.dot, or if you're using Python 3, you can use the @ sign to do a valid matrix multiplication, or you can use dot on a vector, where the vector is an object, so we can call a function using the dot notation. Also, for matrix, the same holds. So we can pass both A and B into the dot function, or we can use the @ sign, or we can use the object-based dot notation. Now, in addition to dot products, there is a variety of functions in NumPy that can speed up our implementation of various algorithms. For example, if I want to take, let's say my matrix A is A11, like this, and what if I want to raise each one by exponentiating it? So then my result would look like this, e to the A11, and so on. Now I could loop over I and j and raise each one, or I can call numpy.exp of A, and it will raise element-wise all the elements of A by taking e to the A sub ij. The following is a list of all such functions in NumPy that you may find useful for homework 2. And finally, I'll mention a little bit about broadcasting. So what I've got here is a vector, just the numbers 1, 2, and 3. So by first initializing an array, if you call shape, this will return 3, 0. Actually, sorry, the 0 is silent, but it will return 3 and comma in NumPy. But by expanding along the 1th dimension, now we can turn this into a column vector, which looks like this, 1, 2, 3. And if I add this to itself, 1, 2, 3 plus 1, 2, 3, I get 2, 4, 6, like so. Now notice if I take u plus u transpose, that's like this, u transpose plus u. Then the result that Python will spit out is like this, a matrix of 3 by 3. So broadcasting is the capability of NumPy to take copies of a vector, like so, and now add the next one in each of these indices, like this one, plus this one, plus that one, and you get a matrix as a result. So that's broadcasting in a nutshell. Cheers, hope you enjoyed, and good luck on homework 2.